I divide the research aim into 3 research problems. The first one is how to utilize knowledge, because the knowledge is scattered everywhere in a not structured way. So we hope we can acquire the knowledge from various sources, including the national standards, enterprise roles, design cases, expert experiences, etc., and structure all the knowledge and store them in a knowledge management system. The second is how to design efficiently. We hope to come up with an agile design framework so that we can achieve automatic or semi-automatic layout design through the human and the machine collaboration. In this process, we might improve or adopt some optimization algorithms, and the designers can dynamically observe and adjust in real time to guide the generation of layouts which can meet the expectations of the human designers. The last one is how to evaluate the quality. We hope that we can come up with an idea to evaluate the design quality, integrating the subjective and objective methods, because in designing the pipeline layout of the ship, we first have to satisfy some objective methods. For example, the total length of the pipeline should be shorter than some millimeters, or the numbers of bands of the ship should be minimized. But we also have some subjective evaluation roles or requirements. For example, the designers can evaluate these solutions according to their preference for the risks or preference for the appearances. So we hope to come up with a comprehensive evaluation method integrating these 2 aspects. And so this is overview of the overall research approach. And the first one will be the knowledge-driven method. We will acquire the pipeline design knowledge first and decompose the knowledge and identify the key components of the knowledge. And then we'll establish the pipeline layout roles and classify them according to the predefined categories or structures. And we'll identify the key objects from each role. And all of the roles will be classified to identify whether they are constraints or whether they are optimization objectives. So actually there are differences between the constraints and optimization objectives. I wanted to classify it a little bit. So what are the constraints? Constraints are the red bottom lines so that we can never touch when we design the pipeline layout. For example, there are many obstacles such as the air conditioners. The pipelines can never pass through the obstacles. So this will be the constraints. And there are also other requirements, which were the optimization objectives. For example, to save the material cost, we hope that the total length of the pipelines can be as short as possible, but we will not set a very strict requirement on the total length. And in this case, this will be the objective of this design. And in the whole process, we will have multiple constraints and multiple optimization objectives. And then after we extract the knowledge from the knowledge management system, we will go for the agile design. We'll first model the layout space, including the free space and obstacles. And then we will simplify the ship equipment, because the ship equipment are usually of very complex shapes, and we hope to simplify the ship equipment so that the computer can deal with it more efficiently. Then we will come up with some algorithms to look for the paths for the pipelines, and we divide it into 2 major scenarios. The first one is the simple pipelines with only 2 endpoints, the start point and end point. And we will propose some heuristic functions based on the classical algorithms. The second scenario is the branch pipeline. And in this scenario, we mainly focus on the initialization method of the branching point. The branch pipelines will connect multiple endpoints, so it will be more complex. After we obtain the design, we have the quality evaluation process And in this process, we will have the feature design and the network training, because we will use the machine learning algorithm. And after that, we will output the optimal scheme after the selection process. So I would like to introduce our preliminary results a little bit. This is how we deal with our knowledge management system, and this is the overall process. So this is from the expression of piping design knowledge to the construction of a knowledge management system. So we first extract the roles from various sources, including the industry regulations, the company regulations, the experiences of the experts, etc. And then we extract the knowledge from them, and we will construct the ontology of all the knowledge. After that, we will build a system based on the knowledge graph. So we will store all of the data within this system and build this construction. With this system, we hope that we can apply the knowledge more easily. So this is the establishment process of the pipe routing knowledge management system. And this is the architecture of the pipe routing knowledge management system. It is divided into 3 layers. The basic layer is the data layer. So we will have different data from various sources, as we have just mentioned, such as the industry standards and expert experiences. And all of these data will comprise the pipe routing knowledge. And the second layer is the construction layer. So we will build the ontology model, including the concept types and object attributes. And we will also define the structured knowledge database. Within this database, we will define the nodes and define the edges. The nodes will stand for the different objects or different knowledge, and edges will define the relationship among these nodes. And last layer will be the application layer. So with this layer, the users will have some connection with the system through the user interface. So we'll have different functions in application layer, including the user login, the knowledge graph visualization. And within this layer, the users can retrieve the knowledge about the pipe routing knowledge. And what is more, they can interact with the system through the Q&A form. So they can ask their questions in natural language, because it is supported by the large language model. These were the first step of the knowledge management. In this process, we will extract the knowledge from various sources and categorize them based on a common structure. So these are some examples of our engineering roles. I'll explain some of them. For example, the piping layer height have to meet the requirement of 21 millimeters. That is because we have to design some space for the personnel to pass through under or beneath the pipelines, so that the personnel can operate or install or maintain the pipelines in the later phase. And we also require that there should be sufficient installation space for the bolts. And we have just mentioned the pipelines cannot pass through areas that are strictly prohibited. For example, if there are air conditioners or other devices, the pipelines cannot pass through it. And there should be sufficient space for the valve operation, and diameters of the pipelines and connectors should meet the requirement. So we will classify these engineering roles into different categories. Some of them are designed for physical constraints, and some of them are economic considerations. For example, we hope that the length of the pipeline can be as short as possible. This is to save the material cost. So this comes from the consideration of economics. For another example, we require that the bends of the number of bends of the ship pipeline should be minimized, because when we have more bends, the speed of the fluid will be decreased. And it is easier for the ship pipelines to to be broken. So with the number of bands as minimized, the reliability of the system is enhanced. And we have some requirement for the layer height or the difference between or the spacing between the pipelines. This is established for the convenience of maintenance or operation of the personnel. And some of them are just for appearance. So we will classify them into different rows. And after that, after the extraction of the knowledge, they will be represented into different structures. And I'll offer you two examples. This is the first one, the row core component 1. And we categorize this row as the structure. Do object A and object B satisfy row C? This is the first example. Does the spacing between pipeline welds meet 15 millimeters? And in this example, the weld A will be the object A, weld B will be the object B, and the distance between these two objects will be our row C. That is, the distance between these two welds should be larger than or equal to 50 millimeters. For another example, we require that the pipeline spacing should meet 20 millimeters. And in this case, the pipe A and pipe B will be the two objects, and the distance between these two pipes will be our row C. And these two examples are similar as well. And this is our second structure. We categorize the row as does the attribute B of object A satisfy row C. And I'll offer you 3 examples as well. The first one is that, does the layer height of the pipeline meet the requirement of 2,100 millimeters? As we just mentioned, this is to design some space for the walking of the personnel. So in this case, the object A will be the specific pipe, and its attribute B will be the layer height of this pipe. And row C will be the space height of this object. So it should be larger than or equal to 2,100 millimeters. And we also require that there should be sufficient installation space for the bolts, because when installation space is too small, it is very difficult for the workers to install or maintain the bolts afterwards. So the object A will be the bolt, the attribute B will be the installation space of this bolt, and the row C will be some requirement on the space. For example, it can be larger than or equal to 50 millimeters. So after we have these structures, we create the class and create the properties of this knowledge, and we build the entity of all of the rows. As you can see, they are categorized and stored in a hierarchical structure, and these are the nodes, and these are the edges. So every object or the attribute are stored in the nodes, and the edges will stand for the relationship among these nodes. For example, this is object is the distance, and it includes the distance between the pipelines or the distance between the pipeline and the wall or cabin of the ship. And in this way, it is very easy for the designers to look for a certain structure or a certain role and to understand the relationship between this object and attributes. So we store this in this graph structure with the help of this new 4J graph database. And this shows how we can retrieve the knowledge from this system. This is the graph that storing the knowledge that we have just mentioned. The people can search for any keyword so that it's easy for them to find some certain rows, and they will also find the related rows. They will find the rows which are related to the specified rows they are searching for. And the right one is a Q&A system. So in current practice, the junior designers usually consult the senior engineers to learn for the design rules or design regulations. but it's very consuming and it's tedious for the senior engineers to invest a lot of time on the training of the junior engineers. And it's also hard for the junior engineers to obtain the knowledge they want to learn about in an efficient way. So we developed this Q&A robot or system based on our knowledge base. So in this system, the junior engineers will see some predefined questions, and they can just click on the predefined questions, and the robot will answer them directly. They can also choose to type in questions they are curious about. And in this case, the robot will acquire their knowledge, look for their answers in our database first. In case the knowledge can be found in our database, the robot will answer them directly. However, we will also have some cases that the questions cannot be found in our database. Then in this case, the robot will search on the internet and answer them using the large language model. We have also have some constraints on this Q&A system. In case that the junior engineers are asking questions beyond scope of ship pipeline layout, the robot will directly answer, sorry, I don't know, to avoid some strange or weird answers. So after we extract all of the important knowledge from the Q&A system, we can conclude 10 most important engineering roles and begin our pipeline layout design. So how do we achieve it? The first one is that we need to model the ship space. So we use the grid decomposition to stand for the ship space to facilitate the operation of the computer. And then we model the ship equipment. For example, this equipment is of some complex shapes. And we use some simple shapes as the bounding box to stand for it. And then we use the center line of the pipe to stand for the pipeline. And then through the Q&A system, we obtain 10 most important engineering roles. And we classify them into constraints and objective functions. For example, these are the red bottom lines. The pipeline need to connect the specified interface while avoiding obstacles, and it should be perpendicular to each other. So these are classified as the constraints. And then some are classified as the objective functions. The pipeline should be as short as possible. The band numbers should be minimized, and the distance to the wall should be closed to facilitate the installation of the supporting structure. And they should be close to the equipment as well. And then we establish a mathematical model for the pipeline layout by expressing these 5 objectives and 5 constraints. And here we improve the classical and cloning algorithm. It's a traditional heuristic algorithm to find the path. But in the traditional and cloning algorithm, it's easy to fall into the local optimum, and the search efficiency is not high. So we improve it in these 3 aspects, including the searching strategy, the path optimization strategy, and the pheromone update roles of this algorithm. And in this process, in the existing and cloning algorithm, this Q0, which can be seen as the threshold, it's a constant, but in our algorithm, we make it dynamically changeable. So it can adjust the algorithm's ability to optimize and explore and keep a balance between the searching efficiency and the quality of the final solution. And we also change the algorithm to increase the directional guidance of the goal so that the total length can be shortened further and the elbow can be reduced. We also add another strategy, which is called the special structure check, because we will check the structure after we finish one iteration. You can see that this is a redundant pocket. So we will remove this so that the total length is shortened and the number of bands is shortened as well. And we perform some simulation cases to verify the feasibility and the superiority of our algorithm. And this is a scenario adopted from the literature. And these are the solutions of the literature, and these are the solutions of our algorithm. And you can see that some schemes are identical, and some schemes are only slightly different from each other, but the performance indicators are the same. However, the convergence speed of our algorithm is increased by over 6 times. This is another scenario as the case study, and the layout quality and convergence speed are both increased. These are how we are dealing with a branch pipeline layout. In the current algorithm, this is a fixed point, but in our algorithm, we make it dynamically changeable according to the iterations of our algorithm. This is how we set it, so it can be updated dynamically. And these are our case studies. As you can see that the convergence speed is increased a lot. The layout quality is increased as well. These are some increasement of our performance indicators, including the increase in the decrease in the length and the decrease of the total number of bits. And we also developed a system to visualize our searching process. This is how the pipeline will grow along these directions, and these were the values of the key performance indicators, so that evaluation is much easier. So I would like to conclude my presentation. We have established a knowledge management system and developed a mathematical model for the pipeline layout design. We proposed an automatic pipeline layout method, which increased the efficiency and decreased the design cost. And we have also achieved the visualization of the search process. I think this is the end of my presentation. I would like to thank the opportunity of sharing my research in this fantastic summit again. And thank you a lot for your time.